Okay, so last day what we have discussed is the properties of systems, right? We have discussed different types of properties like stability, causality, then the linearity, right? Time invariance. Apart from that, the memory less and the memory based kind of systems we also discussed. Now, while we ended last day, we mentioned that a silence. Last bench. So while we ended last day, we discussed that although these different properties are independent of each other. For example, the linearity has nothing to do with the stability. Stability has nothing to do with the causality, or the linearity has nothing to do with the time invariance. But if I incorporate this linearity and the time invariance together, then we can get a new type of system which we call a linear time invariant system, or linear in general it should be called like a linear shift invariant system, LSI. Because in our case, since we are dealing with the signals which are functions of time, so that's why the shift, the term shift is invariably time, right, for our case. Because in my very first class, I told you that although we regard the signals as a function of time, but there is no point to consider signal as a function of time only. Signal can be function of anything. Signal can be function of space, signal can be function of any other parameters in practice. But in most of the cases, we deal the signals as a function of time. So therefore, the generic term shift can be regarded as time in our case. Okay, so that's why although the term is like linear shift invariant, but in our case, the specific one, we consider it to be a linear time invariant system, right? So we know that linearity is having two different segments. One is known as the additivity, second one is known as the homogeneity. And once again, this additivity and homogeneity, these two properties are independent of each other. So you can have a system which is additive but not homogeneous. You can have a system which is non-additive but homogeneous. You can have a system which is both additive and homogeneous, and you can have a system which is neither additive nor homogeneous. So out of these four different combinations, so if you have both additivity property as well as the homogeneity property, then we call the system as a linear system. And lastly, I've given some examples for that. A system can be additive but not homogeneous, can be non-additive but homogeneous, right? Non-additive, non-homogeneous, and additive and homogeneous. And if the system is additive and homogeneous, we call the system as a linear system. That means it follows the superposition law, theory of superposition, and then if we incorporate invoke the property of shift invariance or time invariance, then these two properties together, linearity and the time invariance together, we call the system as a linear time invariant system, or in short, LTI system. Okay. Apart from that, we have also discussed the stability, Vivo stability, and the causality, and the memory-based system, something like that. So that way we have ended with a note that this linear time invariant system, typically we deal with the linear time invariant system mostly. So there are certain reasons for that. So to start with, so today we will discuss this LTI system from two different perspectives. So let us start with the discrete time signal first, right? Then we will move our discussion to the continuous time signal. So for example, suppose I am having a linear time invariant system for which the input is given by x of n. You know what is meant by x of n? Discrete signal, discrete sequence. So suppose this is represented like, say for example, suppose this is the bounded one, the fixed length sequence. So let's call it -1, then 2, then 5, then 4, then 7, then -3, and suppose that is the end. That is the sequence. So we have 1, 2, 3, 4, 5, 6 elements, and let us assume that the x of 0 is this one. This is x of 0. Typically, this is identified by this arrow. Whenever you have this arrow, it signifies that this is basically x of 0. Okay. So therefore, this x of 0 is equal to 5. So what I can write? X of 0 is equal to 5. X of 1 is how much? 4. X of 2 is equal to 7, x of 3 is equal to minus 3. Okay, and what else? You have x of minus 1, that is equal to 2, and x of minus 2, that is equal to minus 1. Is it okay? So basically it's a finite length sequence. What is the length? What is the length? What is the length of the sequence? That is 6. Okay. What is the bound? Is it a bounded sequence or unbounded sequence? Bounded sequence. So what is the bound? Sorry, what is the bound? Is it bounded or bounded? So what is the bound? Huh? So what is the bound? What is the bound? We discussed now bounded input, bounded output kind of thing. So it's a, I mean, you have only one answer for that. Is it a bounded sequence? Yes. If it is yes, what is the bound? So last time we discussed a signal is set to a bounded signal if x of t or x of n, mod of this is always less than or equal to m of x for all t or for all n. 7 here, right? That is the bounded sequence, is the bound equal to 7. Okay. So now this is a sequence basically minus 1, 2, 5, 4, 7, minus 3. It's a bounded sequence, right? Bounded sequence and also finite length. So now I can visualize this sequence in terms of some basis functions. What are the basis functions? So these are like you have studied vector now. In your mathematics you have studied the vector algebra and all these things. So you have like unit vectors. I, J, K, you have unit vectors. So you would like to represent any such vector in three-dimensional space. Then using those unit vectors, it will be easier for you to represent those vectors, right? Any arbitrary vector. So these unit vectors are known to be the corresponding basis functions for them. So here, so we have to identify one function. The function we discuss different types of signals, right? Like pulse, impulse, step, then exponential function, different types of functions we have discussed. So can you tell me what out of those different functions that or different signals that we have already discussed in this particular class? So what function can you pick up to use as a basis for this particular signal? So what is the basis? That means it will be used to reconstruct this particular sequence. Out of these different functions that we have already dealt in this particular course, so what function can I select for this? What can I select sinusoidal function? Impulse function. I can select the impulse function, and you know the impulse function. How is it defined? This impulse function delta n. How is it defined? In discrete time. This is given by. It's very easy. Delta n is equal to 1 for n is equal to 0, and delta n is equal to 0 for n not equal to 0. Right? So delta n equal to 1 for n equal to 0, and delta n is equal to 0 for n not equal to 0. So using this delta function, so only delta function you cannot represent, but you have to use the scaled version and the shifted version of it. Scaled and shifted, then you can reconstruct this entire sequence. Okay? Because you know here none of the values, I mean the x of n values, none of the values are equal to 1. Either you have 7 or 5 or 3 or minus 3 or 2 or 4. So it should be scaled. And you know that delta n is, it will exist only for n equal to 0, but it exists for n is equal to minus 2 to 3. So you require shifting as well. So you require shifting as well as the scaling. Okay. So how can I represent the function then, x of n? So this x of n is basically, I can represent this x of n as, this x of n is given by, first you take the first one, minus of 1. Okay. Where it is located? This is located at, it is located at where? N is equal to minus 2. So you have to shift the delta function, the backward direction, leftward direction by how many units? 2 units. So it is basically delta of n plus 2. So I can write like minus of delta n plus 2. Okay, the first element. Next element is 2. So this is basically plus 2 delta n plus 1. Okay, next element is 5 plus 5 delta n. Next element is 4. Now the next element is present at n is equal to 1. So delta is shifted in the positive direction. Right. Previously it was advance, now it is delay. So plus 4 delta n minus 1 plus you have 7 delta n minus 2 minus 3 delta n minus 3. That is a description of the signal x of n by means of shifted and scaled version of the data. Shifted and scaled. Okay, so this is basically minus delta n plus 2 plus 2 delta n plus 1 plus 5 delta n plus 4 delta n minus 1 plus 7 delta n minus 2 minus 3 delta n minus 3. So therefore any sequence, so here we have considered some sequence which will exist only from minus 2 to plus 3. It can also exist from minus infinity to plus infinity. Right. The length of the signal, so here the length is finite, so you can also have infinite signal, infinite length signal. But that signal can also be represented by means of delta function. So in general, any function x of n, any function x of n can be represented, in general, can be represented by this particular form. I call it x of k delta n minus k, where k is ranging from minus to plus infinity. That is a generic representation of any discrete time sequence. Any discrete time sequence x of n, where n is basically the time index, can be represented as summation for all k going from minus to plus infinity x of k delta n minus k. Is the representation clear to you? X of k is basically the corresponding weights. That means like minus 1, 2, 5, 4, 7, minus 3, something like that. And delta n minus k is basically the shift by k units. If k is positive, that means this is basically the delay, and if k is negative, that implies it is advance. Is it all right? Or any doubt? Do you have any doubt? Okay, fine. So this is the signal we are dealing with now, x of n represented by summation k going from minus to plus infinity x of k delta n minus. Okay? Now with this understanding, now let's move on. So now let's consider we have a system. We have a system S, and let's consider, okay, let it be an LTI system whose input is x of n, and that x of n is given by summation k going from minus to plus infinity x of k delta n minus k. Okay, try to understand how do I represent this x of n and x of k. X of, when I represent x of, that is basically the notation in the language of signal processing or signals and systems. When you represent the signal as a function of something, so this is represented in brackets x of n, and when this is a constant, then it is represented using a parenthesis x of k. X of k, once again delta n minus, that is a function of time. X of n is a function of time, delta n minus is also a function of time, but x of k is constant. For fixed case, this is constant. Okay, so that is basically being fed to an LTI system, right? Now let's move to that particular question, that why this LTI system is so much important to us. Although linearity is something, because I have given you example that the linear system is very difficult to visualize in practice. Even if you take any example from the external world, it's very difficult to correlate some system which is linear in nature. It's very difficult. I have given you an example. The systems that we typically look around us, the systems are not also the time invariant. Typically, they're time invariant system. Okay, but still we prefer the linear time invariant system to deal with. There are certain reasons for that. Obviously, one thing is that it is easier to analyze this kind of system, and there are certain reasons behind that. What is that? What is that reason? So, while we have what is our basic object? Suppose we have a black box, right? You have a black box. You know that this particular black box will perform some activity. Okay. So what do you want? As a layman, you'd like to know everything about the system. You'd like to explore the system. What is the property of the system? Whether the system is a causal, whether the system is a stable one, reverse stable one, whether the system is for any given input, what should be the output of the system? You'd like to know everything about the system. That means you'd like to characterize the system. You'd like to observe the system from different perspectives. That means you have basically learned the system. What is the system all about? Right? And while doing that, since people are lazy, typically, so you prefer to know everything about the system just by doing the minimum effort. What would have been the ideal exam scenario for you? Give minimum effort and get the maximum benefit out of that, isn't it? Get the highest grade. S, get the highest grade. In our examination system, S is the highest grade in theory or lab. That is the highest grade, and you prefer those subjects for elective papers, for selecting elective papers. That will give you the highest grade. The highest grade is S. Using minimum effort. You study for 2 hours before the exam and you will be getting S. You prefer that kind of subjects, no? On the other hand, suppose I am giving another example, say you have to study for say 40 hours and then it's very difficult for you to get a grade of B or C. You will be afraid to opt for that particular subject. Right, so people are lazy. So, while characterizing the system, you'd like to know everything about the system. Everything. All the properties you'd like to explore about the system. Using minimum effort. So, what could have been the minimum effort? At least you have to perform one experiment you have to perform on the system. Because you cannot do less than one. You cannot perform fractional experiment. This is not possible. When you perform an experiment, either one experiment or 2 experiments or 5 experiments, the thing is that the minimum one could have been 1, at least 1. Okay, so LTI system is that kind of system for which you know everything about the system just by performing a single experiment. You perform a single experiment on it and you know everything about the system. That is the beauty of LTI system. Only one experiment, you have characterized everything. Now the question is that what is that one experiment? What is that one experiment which you are supposed to do to know everything about the system? The thing is that experiment is you have an LTI system or LSI. You would like to characterize the system. What is that single experiment? You excite the system with delta n or delta t. For continuous time it is delta t, for discrete time it is delta n. You excite the system with delta n. Okay. That is impulse input, unit impulse input. What should be the output? That is the impulse response. This is called impulse response. The response due to the impulse. Typically represent by means of h of n or h of t. So that is the single experiment. And you have selected this signal delta n. Because delta n possesses one very beautiful property and unique property that is not exhibited by any of the signals available on the earth. Delta n is that particular signal, which you will understand what is that particular property when we will move to the frequency response of the signals and systems. Then you will understand. Basically, delta n, this delta function or impulse function, contains all the frequency components in equal proportion. It contains all the frequency components in equal proportion. That is the beauty of the function. So that's why we have selected, we have picked this delta function, delta n, and we feed this delta n as an input to the LTI system to get the output. We call it impulse response, h of n. And once you perform this experiment, once you get h of n, once you know what is h of n of the system, then you know everything about it. Everything about the system is known to you. Whether the system is a stable one, whether the system is a causal one, whether the what for a given input, what should be the output, everything is well. Whether the system is a memory-less system or memory-based system, so everything about system is known to you if you know what is the h of n for that particular system. Clear? So that is a kind of description. Now let us try to understand whether this is actually true or not. Now suppose the system that we have an LTI system, and we know that for this particular system the impulse response is given by h of n. Okay. Now the input to the system is not delta n. What is the input? Input is x of n, which is given by summation over k equal to minus 2 plus infinity x of k delta n minus k. This is not equal to delta of n. But you know what? You know h of n, and you need to find out. The value of the output. We call this output as y of n. What is this y of n? If the input is x of n, output is y of n. If the input is delta n, output should be h of n. But here the input is not delta n, but the time shifted and scaled version of delta n and added together. Summation over, so what you have three different operations done over there. First operation is basically that you have the delta n and then the delta n is shifted either in the positive direction or in the negative direction, delta n minus k. Then each of these delta n minus k, they are multiplied with x of k. And then all these weighted shifted delta functions are added together. So basically you have three operations involved already. One is the shifting of the delta function, either positive shifting or negative shifting, followed by the multiplication with the factor x of k, followed by this summation, addition. And now we try to identify the three operations, the three properties of an LTI system. What are those three properties we have discussed? What are those three properties? Addition, additivity, homogeneity, and shifting variance. And here, what we have done, we have represented this signal x of n in such a way that it incorporates all these three operations. Delta n minus k, that means it gives you the notion of shifting, right? Shifting. X of k multiplied with delta n minus k, that gives you the notion of homogeneity. And then the summation sign outside, that gives you the notion of additivity. And you know that the system is an LTI system. That means the system is additive, system is homogeneous, system is time infinite. Okay? And you know what? You know, if delta n is my input, h of n is my output. That you know, because you have already performed one experiment. Right? Now, what is your input? Not delta n, rather delta n minus k. So, let us assume that you have the system characterized by h of n, and the input is basically delta n minus k. Right? What should be the output? The system is characterized by the impulse response h of n. Your input is not delta n. If the input is delta n, output should be delta h of n. But here the input is what? Input is delta n minus k. So what should be the output? H of what? Which property you should apply here? This is an LTI system. Out of these three properties, additivity, homogeneity, and shift invariance, which property? Because you know that if delta n is input, H of n is output. That you know. There are three properties: additivity, homogeneity, and time invariance. So out of these three properties, which properties? Out of these three, which property you are going to apply here? Which one? Huh? Time invariance property. So, what is the description of the time invariance property? Yeah, that means if the input is shifted by some amount, you'll be getting the same output shifted by the same amount. Right? Input was delta and output is h of n. Input shifted by k units. The output should also be shifted by the k units, the same output. So what should be the output? Huh? H of n minus k. H of n minus k, right? Is it alright? Is it clear? This only happens if you have an LTI system or if you have a time invariant system for this particular case. If not, then you cannot get h of n minus k. Since the system is a time invariant system, so for an input delta n minus k, you will be getting h of n minus k. Okay. Now suppose the same system, h of n. Now your input, already you know is delta n minus k. Now I multiply this with x of k. X of k delta n minus k. What should be the output then? Which property you should incorporate here? Which property you should apply here? Already you applied that time invariance property. Only two are left, additivity and homogeneity. So which property? Homogeneity. So what should be the output then? You know that for delta n minus k, output is h of n minus k. So for x of k delta n minus k, the output should be x of k h of n minus k. Right? Here. Now what is your actual input? What is your actual input? Your actual input is neither delta n minus k nor x of k delta n minus k alone. Rather, your actual input is basically the summation. Your actual input is basically the summation k going from minus to plus infinity. Only one property is left, the additivity property. What should be the output? Summation outside. K going from minus to plus infinity. And that is equal to y of n. That is y of n. Is it right? So for any arbitrary input x of n, any input x of n, you know, if you know what is h of n, then it is easy for you to say what is y of n. Is that point clear? Yes or no? Yes. Okay, fine. So we have write a very important relationship. Y of n is given by summation x of so we have got this signal x of n, that signal, and h of n minus k. K is ranging from minus to plus infinity. Y of n is equal to summation x of k h of n minus k, k going from minus to plus infinity. Okay, and that particular operation, it involves basically four different operations. One is known as the, so basically I can also write this as, so what you have this particular system h of n characterized by this impulse response h of n, and this is excited by a signal x of n, and it produces an output is equal to y of n. So this y of n is obviously, it's a function of, it should be a function of x of n and h of n, right? And that operation, the summation x of k h of n minus k, that operation, in brief, we represent the operation by this particular notation, x of n star h of n, and this operation is known as the convolution operation. Convolution operation. Which one? This one? Okay, so you have this system h of n characterized by this h of n. Now you have given the input as x of n. You know the output is y of n. So output is what? Output is the input and the system property, right? So you have already seen that y of n is equal to summation x of k h of n minus k. So it involves, so this y of n can be regarded as a function of x of n and h of n. So x of n is the input and h of n is the system property. Okay, so that can be regarded as function of x of n comma h of n, something like that. And mathematically, this can be represented as x of n star h of n. X of n star h of n, and that star is not the multiplication. Remember, this is not the multiplication. We have already studied the dot operation, right? Dot operation. Dot means what? You have x0 multiplied with h0, x1 multiplied with h1, x2 multiplied with h2, something like that. This is known as the dot operation, multiplication operation. But here, we have not considered the dot operation, rather a star operation, star. Okay? And this operation is known as the convolution operation. So this convolution is represented by summation overall k, x of k, h of n minus k. And this operation involves four. So what you have this x of n and h of n. And when you represent this, or you can also write like, okay, notationally you can write something like that. Then when you observe this signal over here inside this entire representation, you have x of k and then h of n minus k. So you have started with h of n or h of k, whatever it may be. So it involves four defined operations. What are those four operations? The first operation is the time reversal operation from h of k to h of minus k. Okay? H of k to h of minus k. And then the multiplication operation, x of k with h of, or h of minus k, if you consider n is equal to 0, that is okay. If not, then after time reversal, you have some shifting as well, h of n minus k. And then you multiply this with x of k, and then you add all those operations, all those values. So this convolution operation, it involves, is basically an operation between two signals. This is an operation between two signals. Discrete time convolution, it is an operation between the two signals. And then what is the value where you are getting, how to find out this value? You have one signal. Let's consider the h of n is the signal. You just flip it, take the mirror image. Okay? Reflection. Then shifting. Then multiplication. Then addition. We call it folding, shifting, multiplication, addition. So this convolution involves four individual operations: folding, shifting, multiplication, and addition. Four operations. Okay. And finally, for an LTI system, the output of this system is given by the convolution between the input signal and its impulse response. It is not that the convolution only exists over here. You can always convolve one sequence with another sequence, one signal with another signal. But when it comes to an LTI system, then its output is related to its input by virtue of this convolution operation. That means your output is given by the convolution between the input signal and its impulse response. So, if you know the impulse response and if you know the input signal, then you will be able to find out the output signal. Is it okay? So now let's take an example. Let's take one example. So let's start with the discrete sequence so that it will help you to understand the concept properly. And let us consider all the signals to be a causal signal. Okay, causal signal. So it starts from 0 only. 1, 2, minus 4, and then 1. Over here, this. And h of n is given by, say, 0, 1, 2. Make it simple. Or I can make it 0, 1, 3. 0, 1, 3. Is it okay? I have two sequences. Your input is given by 1, 2, minus 4, 1, and the impulse response given by 0, 1, 3. I need to find out the output resulting from this when the impulse response of this LTI system is given by 0, 1. Remember, impulse response of the LTI system. Even if your system is non-LTI, then also you can have some impulse response. But that doesn't characterize the system. Make no mistake. What we want to emphasize is that it's not that for all systems, the output is basically the convolution of the input and the impulse. Only if the system itself is an LTI system, then only you can have this convolution operation. But even if the system is non-LTI or non-LSI, then also you can find out the impulse response. Nobody can stop you. You have one system, you put the impulse as an input, you'll be getting the output as the impulse response, but that doesn't characterize the whole system. And that is the beauty of the LTI system. You just perform one experiment and you know everything about the system. Do the minimum effort and get the maximum out of it. Okay. So that is the entire story is for an LTI. Remember this, the entire story is for an LTI system. Even if it is non-LTI, you will be getting some h of n. But then you cannot find out the output by the convolution between the xn and h of n. Okay, so let's do some graphical approach first then. Okay. So let's start with x of n. So let's draw x of n first. So this is your time axis. This is your time axis. That means it signifies t is equal to or n is equal to 0 here. This signifies n is equal to 0. X of n 1, 2, minus 4, 1. 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 This is n basically. This is x of n. Okay? What about h of n? You know, 0, 1, 3. So this is basically x of n. And then you have h of n, 0, 1, 3. 0, 1, 3. Better if I reduce this height. Otherwise, very difficult for me. One, 2 minus 4, 1. One, 2, minus 4, 1. Now let's consider the sequence h of n. How does it look like h of n? 0, 1, 3. So 0 there, 1 there, and 3 there. This is h of n. Okay, so how to find out the output? How can I find out the output? So there are two operations. You visualize this x of n, as I did previously. You visualize this x of n as the scaled and time shifted version of the delta function. Scaled and time shifted version of the delta function. So over here, what you can do, let me consider, okay. Let me draw here only. Small. First we consider x of 0. What is the value? I mean, I can always represent this one as this x of n. You can always represent it. You can always represent this x of n as delta n plus 2 delta n minus 1 minus 4 delta n minus 2 plus delta n minus 3. Is it all right? And you know h of n is equal to 0, 1, 3. So if you provide delta n alone to the system, what should be the output? Let's call this output as h of n. So if this is the input only delta n, what should be the output? H of n, that is 0, 1, 3. So let's call this as y1 of n. This y1 of n is given by 0, 1, 3. Any doubt? Last but one bench, last but one. Any doubt? So the first component is given by 0, 1, 3. Okay? If my input is delta n. The first input is basically delta n, x of 0. What is the second input? 2 delta n minus 1. Okay. So what should be the output? For 2 delta n minus 1, what should be the output? Let's call the output y2 of n. So what should be this y2 of n? The second output y2 of n. It should be for delta n, for the input delta n, output is h of n. For the input delta n minus 1, output should be h of n minus 1. For the input 2 delta n minus 1, output should be 2h n minus 1. So how to get this 2h n minus 1? So you have to multiply this with 2 and shift by 1 unit. Okay? So 0, 2, 6 and located and starting from 1 only. So 0 here. So here you have the arrow. 0 here, 2 here, 6 there. y2 of n. Okay? What should be your y3 of n? y3 of n. Multiply this with minus 4. Multiply this with minus 4. This is 0, 1, 3 and shift it by 2 units. So minus 4 means what? 0, minus 4, minus 12. Start from here. 0, minus 4, minus 12. Okay? And the final one. I don't know whether I'll be able to anyway. So let's draw there only y4 of n. What is y4 of n? 0, 1, 3, right? 0, 1, 3. Right? So you have found out the individual components resulting from the individual inputs. So you can divide your input to 3 different, 4 different segments. One is delta n, second one is 2 delta n minus 1, third one is minus 4 delta n minus 2, fourth one is delta n minus 2. And calculate the individual outputs. Y of n, y1 of n, y2 of n, y3 of n, y4 of n. And because of the additivity property, now you add sum them up. Right? So what should be the final output then? If you add them together, what should be your y of n? Y of n. What is y of n? What is y of n? At location 0. At location 0, what should be the final output? Add them together, it will be 0. At location 0. Next one. This is 1. Next 5. Then 6 minus 4, 2. Next minus 11. Then 3. That is the final output. Okay? 0, 1, 5, 2, minus 11, 3. Okay? So while arriving at this particular result, we have divided the actual input, we have represented the actual input as the time shifted and scaled version of the impulse function. Summation over x of k delta n minus k. We found out the individual outputs due to x of k delta n minus k. Obtained the individual outputs like y1 of n, y2 of n, y3 of n, y4 of n, and then added this. Right? That is the one approach of calculating this one. The second approach could have been the graphical approach. The graphical approach. Graphically, what you can do, you already know x of n and h of n, and you just find out, you just consider the operation too early for the next class. The class is from 12, right? Anyway. Okay. So now let's follow the graphical approach. H of n already we have got like 0, 1 and 3. X of n is given by 1, 2, minus 4 and 1. So for graphically, what you can do, first of all, you need to fold the signal. Right? You fold the signal H of n. You fold this signal H of n, and we call this signal as H of minus n. How does it look like? H of minus n. How does it look like H of minus n? I am going to represent H of minus n. Now cross talk. What is H of minus? How does it look like H of minus n? H of minus n from minus 2 to 0. Here this value is equal to 0. Then you have to take the mirror image. Mirror image. So there you have 1. There you have 3. This is H of minus n. Right, first, second, third bench. These guys. What is the problem with it? Yeah. So each of them you have depicted. Okay. Then what? Just consider the formula. What was the formula? Y of n is how much? X of k, h of n minus k going from minus to plus n. Right. X of k. So there we have used the k as that particular shift element over there. X of k delta n minus k. Or you can also consider, okay, you have like, instead of representing x of n and h of n, you can also represent this by x of k and h of k. Nobody can stop you. So instead of doing that, what you can do, let's make it k. I can only change the naming over there. Xk, hk, h minus k and so on. Okay? Here also. Let me write down the formula over here. Y of n is given by summation x of k h of n minus k. K from minus to plus infinity. So, if you would like to find out y of 0, that means what? You have to put n is equal to 0 in this particular equation. What is that? Y of 0 means the value of this at n is equal to 0. Value of y of n at n equal to 0. So already you have one signal x of k, you have another signal h of k. So either you can represent in terms of h of n or h of k, x of n or x of k. So accordingly, the naming can be changed. Okay. Then what I am doing, I am just reflecting the one signal with respect to t is equal to 0 and k is equal to 0 and n equal to 0. I am reflecting one signal. So here I am reflecting what? I am reflecting h of k. I can also reflect x of k. I am coming to that. So as far as the formula is concerned, I am just reflecting h of k. I am getting what? I am getting h of minus k. I have got this. I have got x of k, I have got x of h of minus k, and this is basically the multiplication. There is no star sign. Between these two, you have pure multiplication, x of k and h of minus k. Simple multiplication, a into b, something like that. So I consider this signal with this signal and multiply them element by element. At this point, at this point, this point, this point, this point, this point, just multiply. Right? And then you add for all k. You have summation for all k, no? Minus to plus infinity. So do you have any overlapping over there? Any overlapping? At 0 only. At 0 you have, because at 0 you have x of k component, at 0 you have h of minus k component. Right? At 0 you have this overlapping. So you need to multiply this x of k with h of minus k only at k is equal to 0. Or other values, the values are 0. So either h of minus k equal to 0 or x of k equal to 0. So here you see x of k is a causal signal, right? H of k is a causal signal. So therefore h of minus k is an anti-causal signal. H of k is causal and h of minus k is anti-causal signal. Therefore, if you find out the overlapping between x of k and h of minus k, the overlapping appears only at k is equal to 0. And one value is 0, the other value is 1. So if you multiply them, the result is 0. So you have got the first sample value, that is 0. Verified, first sample 0. Now what you need to do, you would like to find out what? Suppose you would like to find out the values for y of minus 1, y of minus 2, y of minus 3, and minus 4. That means what? That means what? Meaning what? Y of minus 1. Meaning what? That means already I've got h of minus k. Okay. And then if you shift this h of minus k in the left hand direction, so do you have any overlapping? No. So these values will be 0 altogether. Right? Then if you would like to find out the value of y of 1, that means the value of y of n at n equal to 1. What you need to do then? You just look at the formula. Formula says that y of n is equal to summation k equal to minus 2 plus infinity x of k h of n minus k. So you have got x of k, you have got h of k. From h of k you find out what is h of minus k. And then you need to find out what? Y of 1. So in order to find out y of 1, you need to shift this h of minus k in the right direction. So you can write like h of minus k minus 1. H of minus k minus 1. This is basically h of minus k and h of minus k minus 1, or h of 1 minus k. So how does it look like h of 1 minus k? I believe space is limited, so make it over here. This is once again k, and I would like to find out h of 1 minus k. How does it look like? You shift this entire thing by 1 unit in the positive direction, right hand side direction. So there you have 1, there you have 3, and here you have 0, called h of 1 minus k. Okay? Alright. H of 1 minus k. Now you do the same thing. Find out the overlapping. Do you have any overlapping now? Yes. For how many samples? 2 samples. Multiply them and add them together. Multiply 1 with 1, 0 with 2. Add them. Resultant value is 1. Verified. Next, what you do? Next, you shift this entire thing by additional unit, and let's call it h of 2 minus k. How does it look like then? 3 here, 1 here, and 0 there. We call it h of 2 minus k. Right? Overlapping between 3 samples now, right? At n is equal k equal to 0, k equal to 1, k equal to 2. At k equal to 0, what is the multiplication value? 3 multiplied with 1, that is 3. At k equal to 1, 1 multiplied with 2, that is 2. And at k is equal to 2, this is 0 multiplied with minus 4. So 3 plus 2 plus 0, that is 5. Verified. Okay. And space is limited, so I can show you with the next sample only, and you can verify the others very easily. Here it is k once again. Now you have 3 there, 1 there, 0. We call it h of 3 minus k. Now it is between 1, 2 and 3. Sample 1, 2 and 3. Right? N is equal to k equal to 1, k equal to 2, k equal to 3. So k equal to 1, 2 multiplied with 3, that is 6. And for k equal to 2, this is minus 4 multiplied with 1, that is minus 4. 6 minus 4, that is equal to 2. Right? And you have to perform this process until unless there is no overlapping left. Right? So this is for h is equal to, this is for n is equal to 3. right? Then you have to shift by 1 unit again, and then another unit. H 4 minus k, H 5 minus k. And H 4 minus k until you get, if you shift it further, then this 3 gets overlapped with minus 4, gets multiplied with minus 4, and this 1 gets multiplied with this 1. So 3 multiplied with minus 4 will give you minus 12. 1 multiplied with 1 will give you 1. So minus 12 plus 1 will give you minus 11. So there the overlapping between k equal to 2 and k equal to 3 between these two samples. And then finally if you find by another unit, then the overlapping takes place only at k is equal to 3. Okay, and then the resultant value will be 3 multiplied with 1. Only one overlapping, 3 multiplied with 1, so the value will be 3. So ultimately the resultant value that we are getting over here, y of n, gets validated by two different approaches. This approach is known as the graphical approach, this approach is known as the analytical approach. The left approach that we have done is an analytical approach. You know what is happening inside. Anybody can do this one. Anybody can do this. This right hand approach can be done by anyone. Any civil engineers, any production engineers, any mechanical engineers can do that. Simple graphical approach. Even the class 10, class 12 students, they can also work on this one. Right. But the left approach, the approach that we have done over there, that's an analytical approach. You have to understand what is happening over there inside the system. And this analytical approach and the graphical approach, they get validated. Right? Anybody having any doubt in understanding this one? Please raise your doubt if you have any. Yes or no? Complete understanding or partial understanding or no understanding? Partial? Huh? Full understanding? For all of you? Okay. So that is all about the convolution. The thing that you have done over there, na? The right hand side, the mathematical, the analytical, the graphical approach that you have performed over here, that gives you the flavor of convolution operation. You can always take any two signals. Suppose one signal is x1 of n, second signal is x2 of n, and you can always convolve between these two signals. Similarly, you can also add two signals, x1n plus x2n. You can add two signals. You can multiply two signals x2n with x1n. Similarly, you can also convolve one signal with the other, and that is the method of convolution, the process of convolution. How you can perform the convolution. Okay, and if your system is an NTI system, and if you know the impulse response of such a system, then finding out the output is basically the convolution between the impulse response and the input signal. Yeah? Okay, fine. So let's move to the next phase of this discussion. Well, so what we have found out is y of n is equal to summation k going from minus to plus infinity x of k h of minus k, and this operation is known to be a convolution operation, right? Now the question is whether this convolution operation is commutative in nature or not. Do you mean what is meant by the commutativity of any operation? Yes or no? Can you give me an example of an operation which is commutative in nature? Huh? Multiplication, addition, division, subtraction. So just like any other operation, multiplication, addition, subtraction, division, whether this convolution, whether it is commutative or not, that you have to check. Right? So we have represented y of n is equal to x of k, h of n minus k, and we call this as x of n convolved with h of n. Okay. Now to check whether the operation is commutative or not, so let us put n minus k as m and try to substitute over there. So if n minus k is equal to m, and if k going from plus infinity, what will be the range for m? M will go from, okay, plus to minus infinity. I can write like x of, x of, here you have k, so k is basically what? N minus m, h of m, right? So x of n minus m, h of m. So I can always, since you know that multiplication operation is commutative in nature, so this x of n minus m, h of m can also be represented as h of m, x of n minus m. Okay, and since you know that the additive operation, addition is a commutative operation, so minus to plus infinity and plus to minus infinity will make no change. So m is from minus to plus infinity. Now this equation hm x of n minus m, m going from minus to plus infinity, and that equation k from minus to plus x of h of n minus k, are they similar? This and this. So this can be represented as, if this is as xn star h of n, that can be represented as h of n star x of n. So what is the conclusion? The conclusion is that this impulse response, the convolution operation is commutative in nature. So what is the physical interpretation of this? That the convolution operation is a commutative operation. So suppose you have a system, LTI system, with a given impulse response. Now if the system is excited with any input, arbitrary input x of n, you'll be getting some output. Now suppose the input that you have used last time, this input is used as an impulse response, and the impulse response is used as an input. The roles are reversed. You will be getting the same output if the system is an LTI system. Can you get my point? Since the convolution operation is, so what I mean to say is, so you have a system, LTI system obviously, h of n, characterized by this h of n. This is LTI. And you have excited the system with x of n. So the output y of n is given by x of n convolved with h of n. Right? Now suppose I am having a system, another LTI system, for which the impulse response is given by this x of n, and this is excited with the impulse response of the same. And here the output is y of n is basically the same thing, h of n convolved with x of n. Okay? So if the impulse response of the system is treated as an input, and the input is treated as an impulse response, if the roles are reversed, then the output will be the same. There is no change in the output. Remember, this is true only for LTI system, not for any other system. Clear? So I would like to ask how many of you have understood this concept of convolution in the this entire discussion is the discrete time domain, right? So how many of you have understood this discrete time domain concept? If you have understood this concept, then I can move forward to the continuous time. How many? Please raise your hand. So I guess that all of you have understood the notion of convolution, the notion of finding out the output response for any given input for an entire system is the convolution operation. Now, if you have understood this properly, now let's move to the continuous time. So for continuous time, what we have? We have a signal as a function of time. We call it x of t as a function of t. It's any arbitrary signal. So for the discrete time case, what we have done? We have divided the signal into a number of basis functions. What are the basis functions for discrete time signal? The impulse and its shifted version. Delta n minus k. That is basically the basis function. Set of delta n minus k for all del k, del n minus 1, del n minus 2, del n minus 3, del n plus 1, del n plus 2, del n plus 1. In other words, del of n minus k. Set of all del n minus k for all k. That was the basis function. Using those basis functions, you have actually constructed the whole signal. Right? But remember, for continuous time signal, now the time axis is not discrete. You have the signal present for all values of time. So what could have been the possible basis function now? Is the question clear? Is the problem clear? For discrete time case, we have like x of 0, x of 1, x of 2, x of 3, x of 4 and so on. So accordingly, we have identified delta n, delta n minus 1, delta n minus 2 as the basis functions. But for the continuous time case, what we have, that signal is present for all t. So what is the basis function? So what we can do is, we can suppose the signal is ranging from here to here, t min to t max, dividing this range into very small increments in such a way that the signal amplitude is remaining almost constant in these tiny intervals. Signal amplitude is varying. Now I am dividing this entire range into small intervals. Say one interval, suppose this interval is given by delta t, and delta t is tending towards 0. It's very small. So that x of delta t, or let me write like x of t is equal to x of t plus delta t for all t. X of t is equal to x of t plus delta. That means if you make a change by about delta t, the value of xt remains almost constant. Can you get the point? This value is remaining almost constant. So therefore, now if I exerted this entire thing, so how does it look like? So it is something like that. This is constant. Suppose this is t1, this is t1 plus delta t. Then next interval is something like that. This is t1 plus 2 delta t. Then the next interval is something like that. This time is t1 plus 3 delta t. Basically, I have exaggerated this entire thing so that it looks almost flat top samples, something like that. Okay. So now, had this been the case, and let us mark the samples like, let it be C1, C2, this is C2, this is C3, something like that. These are the constants, C1, C2, C3, something like that. Then, and this entire thing is basically the xt, x of t. Then how can we represent this x of t using some already known functions? Already known functions. Huh? Is it step? Because step exists for all t greater than 0. But this box, it exists only for t1 to t1 plus delta t. These functions exist from t1 plus delta t to t1 plus 2 delta t. This exists from t1 plus 2 delta t to t1 plus 3 delta t. So the duration for each of these is only delta t. Duration is delta t, and with the assumption that delta t is very, very small, tiny sample, I mean the tiny duration, delta t approaching towards 0. Okay, so what could have been the possible signal? That cannot be step, because step exists for all t greater than 0. And here the duration of each pulse, small pulses, are for delta t with an approximation that delta t approaching towards 0. Impulse, right? And what is the strength of the impulse? The strength of the impulse is basically C1 there, C2 there, C3 there. Okay. So, you know this property. If you multiply the impulse or shifted impulse with any signal, and if you integrate this for all time, you are extracting the signal value at this particular distance. Isn't it? So therefore, any arbitrary signal x of t can be represented. So any arbitrary signal x of t can be represented as, you have to find out at t is, say, let us consider one particular interval. Say, let's call this to be, say suppose this is tau. This time is tau, and this time is tau plus delta t. So almost very small, and delta t, the tau plus delta t. It's not delta tau plus delta t. And delta t approaching towards 0. So this value can be regarded as x of tau. This value, this constant value, can be regarded as x of tau. Right. So this x of t can be represented as this x of tau multiplied with this x of tau exists only for t is equal to tau. Isn't it? This is existing, this C1 value is existing only for t is equal to tau to tau plus delta t. Then the value changes to C2, then the value changes to C3, and so on. So this x of tau is constant one. This constant value is existing only for t is equal to tau to tau plus delta t, and delta is very small, it's almost constant. So x of tau, so it's only existing at t is equal to tau. So I could write over here delta t minus tau, and you have so many such x tau over here, right? So you have to integrate for, you need to integrate for all such tau ranging from minus to plus infinity. So that is a description of the signal, any arbitrary signal x of t, by virtue of the shifted impulse function. X of tau, delta t minus tau, d tau, for all tau ranging from minus to plus infinity. Okay, that is a description of the signal. So almost the same description. So last time what I have seen, the only change lies in the integration operation. Once again you have the shifting, once again you have the scaling, you have the addition operation, everything is same. The only change takes place in the, so previously you have the summation outside, this time you have the integration outside. Clear? Now, so let's say you have an LTI system whose impulse response is given by h of t. and the system is excited with some x of t, which is given by minus to plus infinity x of tau delta t minus tau d tau. What should be the output then? Y of t. This is an LTI system. You know that if delta t is the input, the output should be h of t. So if the input is delta t minus tau, output should be h of t minus tau. If the input is x of tau multiplied with delta t minus tau, output should be x of tau multiplied with h of t minus tau. And if the input is like minus to plus infinity x of tau delta t minus tau d tau, the output should be plus infinity h of x of tau h of t minus tau d tau. So this y of t is given by integration over all tau x of tau h of t minus tau d tau. Or you can also represent, since this operation, just like the discrete convolution, since this operation is also commutative in nature, you can also write this as h of tau x of t minus tau d tau. Is it all right? But the problem is that when you calculate, you have calculated the discrete time convolution very easily, sample by sample, and this is not possible here. Because here the time axis is a continuous one. So accordingly you have to find out the range where the mathematical expression being the same, and accordingly you have to find out the mathematically you have to find out the integration. Okay. Okay, so I can give you a very familiar analogy of this one, of this operation, convolution. Remember that convolution is a kind of operation just like any other operation, just like any other mathematical operation. Addition, multiplication, division, subtraction. Between any two signals, you can add two signals, you can multiply two signals, you can also find out the subtraction, the division, all these things. So convolution just like this thing, another operation, another mathematical operation. So to increase the visibility of this operation, the convolution operation, I can give you a very familiar analogy. Suppose there are, say, few people, they are standing on a platform in a sequential manner. Let's try to understand the convolution, the discrete time convolution first. The analogy behind the discrete time convolution. Then you can understand the analogy behind the continuous time convolution. Because if you understand what is discrete in nature, then you can just aggregate them all together, then you will be getting what is the number. Suppose you have say 100 people, 100 number of people, they are present on a platform. Yes, sequential manner, one after another, not in a haphazard manner, sequential manner, 1, 2, 3, 4, 5, 6 on a platform. Okay. And suppose there is a train. There is a train which is entering in the opposite direction, which is entering into the platform in the opposite direction. Typically, the engine enters first. Suppose you have platform, right? So first you have the engine, then the next compartment, then final compartment, last one. But there is a typical train for which the last compartment enters first, and then after the final compartment, the first compartment, the engine enters the last. That means the train is entering in the backward way. Right. Now suppose try to visualize the persons who are standing on the platform. They have their numbers like person 1, P1, P2, P3, P4, P5 up to P100. Right? And there are, and let us assume that there are one person in every compartment of the train. And they are also identified with some numbers. Like T1, T2, T3, T4, say suppose there are 12 compartments or 14 compartments in a train. So there are T1 to T14 or T1 to T12. Now what is happening? The train is entering. So suppose this is the beginning of the platform. That is the end. So P1 there, P2 there, P3 there, P4 up to say P100. Hey, husband. P1 to P100, 1 to 100. The people are standing like this. And the train is entering from that particular direction in the reverse way. So first the last compartment, then the penultimate compartment, and then finally the first compartment, the engine. So there is an operation. The operation is that the handshaking operation between the person on the platform and the person inside the train. And you have to count the number of handshaking operations, the total number of handshaking operations at any instant of time. So the train is entering in the backward direction, and if you have 14 such compartments in the train, so you have 14 members inside the particular train, T14, T13, T12 up to T1. So when the train is just, the first compartment, the last compartment has entered the platform. Or you can also visualize something like that. Although I've told you that there are 100 such people, you can also think that no, there are not 100 people standing in a queue. Rather, they are organized in a matrix form. Suppose in one column there are 5, another column there are 7, another column there are 4, another column there are 9, something like that. They can also organize like this. Total 100, but not sequentially, in a matrix form. 5, then 7, then 3, then 2, then 1, and something like that. Okay, so that it can give you the strength of the signal. It's not always 1. Strength of the signal. Similarly, in the train also, suppose in every compartment, you have say 2 or 3 people, they are standing one after another. Right? Suppose there are say 14 compartments and say there are 50 such members inside the train, 50 such persons inside the train, and they are distributed. 3 persons in one compartment, 2 persons in another compartment, 5 persons in another compartment, they are standing like this. Now when the train is entering in the platform, then the operation is that the persons standing on the platform and the persons inside the train, they will shake hands with each other. And you have to count the total number of hands. Right? If you have 3 persons on the train in one compartment and 5 persons standing on the platform, then how many handshakes you can expect? How many handshakes? 3 persons inside the compartment and 5 persons on the train. Handshaking between the persons inside the train and the persons on the compartment. How many? 15 only. 15 only. Persons on the platform, they will not shake hands with each other. Persons inside the train, they will not shake hands with each other. Persons on the train, they will shake hands with the persons on the platform. Okay. So first the T14, that particular thing T14 with this P1, so this particular row. So that is for n is equal to 0. Then the train is moving. Right? N is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. And this operation is, you have to find out what is the number, and there is no such negative number. All numbers are positive because handshake cannot be negative. Either 0 or positive, cannot be negative. And this operation will continue as long as there is an overlap between the platform and the compartment. And finally the train leaves. When the engine departs from the last end, final end of the platform, then that is the final instance of handshaking. Right? And this is a typical train for which the engine enters, the last compartment, last bogie enters first, and the engine enters last. That means reverse wedding. Have you ever seen the goods train? Goods train you have seen now? So they have this kind of peculiar behavior. Sometimes the forward movement, sometimes the backward movement. Okay, this kind of movement you can see. So this operation. Now you can visualize the person standing on the platform. They can be visualized as the signal. and the persons inside the train, they can be visualized as the impulse response. The handshaking operation with each other can be visualized as a multiplication. 3 with 5, 15. Three members on the platform, 5 members inside the train. 3 into 5, 15. 15 in compartment 1, 12 in compartment 2, 13 in compartment 3, 19 in compartment 4. At a particular time, you add them. How many such handshaking? Add the 19 plus 12 plus 13 plus 15. Addition as total number of counts. This will happen until unless the last, the engine just leaves the final compartment. Now, this is the kind of discrete time convolution, the analogy behind the discrete time convolution. And if you now visualize, okay, the persons are standing in such a manner that this discretization can be considered to be a continuous one, then you can understand what is continuous convolution. Right. So remember that convolution is basically an operation, nothing more than that. Just like addition, multiplication, everything, it's just like an operation. But when it comes to LTI system, whether it's a discrete time LTI or continuous time LTI, when it comes to an LTI system, then the convolution operation will give you the output that is equal to the convolution between the input signal and its impulse response. But you can always find out the impulse response for any system, even if it is non-LTI. You can also get the what is x of t. But remember, for non-LTI system, the system is non-LTI. Then finding out the convolution between the input and the impulse response will not produce the corresponding output. This is only true because that notion is not applicable. So I have written like now x of tau delta m t minus tau. For non-LTI system, delta t minus tau will not produce h of t minus tau. For non-LTI system, x of tau delta t minus tau will not produce the x of tau h of t minus tau. For non-LTI system, the summation will not give you the summation over there. Individual summation will not produce the final summation. Right? So even if the system, if the system is LTI only, then you can find out the output. And if not, then performing only one experiment will not tell you everything out. This is only true for an LTI system. Right? Okay, so with this introduction to this computation of the output for LTI system or a continuous time system as well as for the discrete time system, we have come to the end for so ultimately for this lecture we have come to the end, and we have something to discuss regarding the properties of the impulse, because I have told you last day that this impulse response impulse response can be categorized as the property of the system, can be visualized as the property of the system for LTI system. And I have told you today that okay, there are certain other properties like causality, stability, whether the system is causal, stable, whether the system is memoryless or not. That can be visualized from the impulse response. Yes, it can be visualized, but how is it visualized? That I will discuss in the next class. Okay.